this is a comment on large-scale trends in the ocean that have been observed from temperature profiles in the last 55 years. And if you look in the Atlantic, you remove the average trend, the global average trend, and you look at the spatial differences, and you see that the trend is extremely varying meridionally. There's a huge positive signal in the Southern Ocean near the latitude, the average latitude of the circumpolar current, as is known by other work like Sarah Gill's work from maybe better data, but here there's more data. And that may be related to the SAM, the southern mode, circular mode. But also you see patterns which show something which could be, there is a redistribution of heat over the upper 1,000 meters of the ocean, or more, probably 2,000. And the question is, what part of that would be involving changes of ocean circulation, and what part is maybe changes of exchange at the Earth's interface through the atmospheric circulation, changes in the atmospheric circulation and transport. And if you look here in the Atlantic, average from 55 to 2009, the average, I mean, where this trend comes from, that's in the northern Atlantic. And look more at the red curve, in which I have more confidence than the green curve, which is from NODC, because they had some problems in recent years. You see that there is really a very strong low-frequency signal that's north of 30 north, that's between 30 north and 30 south, and that's south of 30 south, with a huge, a slow increase and then a huge recent increase, which coincides also with the arrival of Argo data. So we're a little bit wondering whether there's still not something there, but I think it's real. You see that also in altimetry, this pattern for the last 20 years. And so you have these very low frequencies when you look at larger scales. When you start looking at slightly smaller scale, like here it's the North Atlantic, and you extract from the last 20 years, or actually it wasn't 20 years, that one, it's only 15 years of altimetric sea level data, which you here see as a proxy mostly of steric content and to a large extent heat content in the upper ocean, not just heat content because salt contributes to it, but this kind of first pattern which shows a change both around the Gulf Stream and the northern part of this intergyre, what some people call intergyre here, and also in the subpolar gyre region, changes of opposite signs, weakening in the subpolar gyre region associated with a strengthening of this intergyre area and a change of position of the Gulf Stream. That's the time series associated to it. It has also these low frequencies, but also when you look at small scale, you start having smaller time scales also. So we'll talk a little bit more about that. In some way, it's related to what Monica talked about this morning about the changes associated with NAO and changes in wind forcing, which forces also the changes in convection in the subpolar gyre and so forth. But we'll come back. One of the issues I'd like to address, or at least I'm interested in, is what are the time scales which are related both to this slightly more regional phenomenon and the large-scale ones, and whether we can see a trace of that in ocean circulation measurements. And here I'll deal only with the upper ocean. But of course, when you look at the longer time scale, you can expect some even larger changes. Probably here is some, it's from simulations there, it's not from data. But that's an analysis of where particles which are entrained to the North Atlantic along Brazil come from where they were first at the sea surface. And from doing a Lagrangian analysis, which is non-divergent, the way you do it, you can trace after some contour of transport, if you want, gives you an idea of the area in the green color to the red color, which is associated with this transport. And in modern time, Sabrina Spetch and colleagues suggest that this transport is really something which they call the large, the supergyre of the Southern Ocean. It's not just the Atlantic. It's something which expands over the three oceans and involves also the Southern Ocean. Looking at some simulation of the last glacial maximum, the situation is completely different. Here, there is also a transport to the north, of course, along Brazil. It hasn't completely stopped, but it comes from an area which is much weaker, much smaller in extent, and is really in the southwest Atlantic, southern Atlantic. So there is these huge changes, and we don't know whether there's not some of the modes of variability. It's a drastic example, of course, but some of these modes of variability involve dynamics of the MOC, maybe of this meridional over oceanic circulation, or dynamics of the ocean circulation in general, and whether they could not be seen to a lesser extent even in recent data. But we don't know about that, but it's a question of what are the timescale over which changes like that, I mean, of this kind of pattern happen. So to start from, I will go a little bit historically after about the measurements on ocean currents, but that's the classical view, a little bit the Harry Bryden view of circulation. Harry is still there, I don't know. But in red, it's the surface circulation. It's really a view which is developed from hydrographic measurements and geostrophy, the application of geostrophy and water mass analysis on sections, CTD section typically. And you see red is the surface circulation, and you see the pattern which is associated to the northward transport of the MOC, but strongly, very strongly reinforced locally in the gyre dynamics, the subtropical gyres and the Gulf Stream recirculation, and the same, you know, for the South Atlantic and so forth. And all this recirculation near the equator, which is very schematically shown. And there's an addition, a recent addition to this diagram, which is to make some of these, two additions. Some of these arrows are really pointed by, you know, little eddies, because what has been noticed is that a large part of the transport in this area, or this one, of the upper water, is really done by eddies, not by average currents. And the other thing is that there is a contribution at depths, you know, of the cold, I mean, the cold route that Harry was describing at 25 south, you know, of water, which is colder and fresher, and which joins this northward transport path. So that's the classical view, but of course, the question we have is, this is something which is kind of an average view based on decades of data. And what does it hide in that as dynamics on shorter time scales, or more regional, or even MOC related, that would be seen, of course, also in the surface, in the near surface data. So another comment is that what one traditionally call as a surface layer in hydrography is something which is, let's say, 500,000 meters thick, sometimes a little less in the tropics, but it's a fairly broad layer. It's a layer over which the surface pressure signals are coherent actually to that depth. So circulation is, with some local, I mean, some changes depending on where you are, but in general, it's fairly coherent over this depth of the water column. So so from this layer, if you want to have data, where you have most data and things which can be really useful to map the variability on most spatial and temporal scales, but only for the last 20, 30 years is really the surface, and for two reasons. We, from the geostrophy, as I was saying, which is what is used for these hydrographic schemes to estimate currents, we have the sea level measurements from altimetry, from which were made to an accuracy which is sufficient from the early 90s to be able to map fairly accurately the changes of sea level slopes across regions that can be used to map changes in currents. And then we have also more general use of drifts of surface objects, ships, drifters. There I have to give an anecdote, which is some personal predisposition to work on that. I worked a lot with drifters. And there is a story, and I was in Rome yesterday where I got stuck, and I thought again about that I was very close, the airport was very close to the Tiber River. And Saint Gilles, when he had his vision and decided to found an abbey near Saint Gilles, which is in the Rhone Delta, at the time was near the sea, was a port in the 3rd century. He went to, in the 4th century, he went to Rome and, asked the Pope, can I fund this abbey? I had this vision and so forth. I saw Christ between us. Anyway, and the Pope gave him the door of the church and he let it float in the Tiber River. And then it drifted across the Liguro-Provençal current all the way towards the Rhone Delta. Already at the time, people knew very well that objects, floating objects, were accumulating in some area of the shore, which could go a long distance. There is also the Saint Mary's de la Mer story also, the wreck which landed there. Because that's an area actually where there's a lot of things going on the coast when the wind comes from the east. Anyway, aparte, but that has been used to estimate currents. Everything put in the water. Now drifters are a big component. There's 1,000 of them put every year in the water, in the world ocean. But the issue we have is the surface layer is sheared. It receives at the Earth's interface the momentum through the wind stress from the wind. And this equilibrates with the Coriolis force to create a sheared layer. And that makes trying to use this data and mixing them with other data like the altimetric geostrophic current rather challenging, actually. But that's something which has been dealt with, and I'll talk about that later on. And then now we have also another component is that we had fairly useful sets of model simulations which are either free. By free, sometimes it's not that free. Sometimes, wind, it's forced by the wind. Sometimes the wind can be varying based on observation. And sometimes also there's relaxation to surface temperature and salinity to some extent, directly or indirectly. And that kind of forces a little bit the variability to some extent. And we have also assimilated runs which start to be really helpful. So we have a lot, and they're helpful, as Harry was saying, mostly in the upper layer. It's true that probably below 2,000 meters, they are much less. Their scale would be much less, but we have very little data to show it, actually, to evaluate it. So a short outline, what we'll talk in the next 30 minutes. I will talk about the tools we have to describe the recent circulation and examples of variability, large-scale features, eddy transport. I'll go from South Atlantic to the North Atlantic, basically. So ship drifts, that's what we have had actually measured fairly systematically since the 1840s. It's really dead reckoning of, over a long time period. So the ship goes a long way, it knows its speed and its heading, and you look at where you are at the end with respect to where you thought you would be, and you estimate from that what the drift due to the current or wind effect on the winds could be. There were also a lot of bottles put at sea, particularly during World War I or just after. During World War I, to see the effect of floating, they started to have floating, exploding device. And they wanted to know, how do you call them? Mines, sorry. And they wanted to know whether they would land on the shore. This was starting to be really dangerous. So, however, all these things, and that's the fairly famous example from Benjamin Franklin's study, where he was interested in getting the mail. I mean, when he was in charge of the mail service to America, he needed to know what the currents were, try to optimize the time it took on going to England and coming back. And he mapped this from the estimates of the ship drifts. But the accuracy is 20 centimeters per second. So it's probably not very helpful to go back through the archive. Also, some attempts have been made in the area of large variability. And now we have these drifters, which measures, I mean, this is one I use, but with salinity measurements also, but the standard version is a little ball, a little smaller than that, linked to a very big drog. It's 8 to 10 meters long. It's made in such a way as to really do a huge drag to the currents, stay in shape, and it's known to be accurate to within 1 or 2 centimeters per second for the currents at 15 meters. And that's examples of what the distribution get over here a 1 year period. In recent years, really, there has been a lot of them. One issue, however, is it's accurate to that when the drug is present, but sometimes the drug falls. And that has been a source of a lot of difficulty in using the data. But to give an example of what we used to have with the ship drifts as maps, that's in the tropical Atlantic, for 2 contrasting seasons, February when the ATCZ is rather far south, and August when it starts to be far north. It's not the furthest north, but it's when the NEC, the North Equatorial Countercurrent south of the ATCZ, is maximum. And that's the view you have for a few years, before there were a lot of drifters actually, a few years of drifters in the area, and you can see that the directions of currents not the same. The differences are typically on this order of, that's 1 meter per second here, so differences are not small, and they are typically of the order of 20 centimeters per second. However, and that's typical when you don't have data, you see waviness like that, which is not real. It's an issue of sampling. But now, over the last 20 years, actually there is enough data to get a fairly reasonable average seasonal cycle from this data. And then there is the sea level altimetry, from which one can estimate anomalies of the sea surface height, and thus the pressure gradient and the current, the geostrophic or cyclostrophic current at the surface. And what you see when you look at such a picture is, well, you see, well, let's concentrate on the Atlantic. You see a lot of eddy structures. Now it's a bit saturated, so you don't see very well the boundary current in that. You would see it if it was a little bit less saturated, because there are some things which come out actually of that. But there are some larger scale structures in the tropic, okay? But what you see is, to a large extent, anomalies on the scale are 100 kilometers and less. So the ocean is full of eddies. That's not new, but that means that to do a reasonable sampling and have features, you need a lot of data. And a lot of data, the only way you have a lot of data, really, is through altimetry. So the big challenge is to try to combine these altimetric measurements with other measurements. In this case, for the surface here, the attempts that have been made up to now, based on data, are really with the drifter speeds, but you could use other things. You could use, and one use now, Argo float profile and so forth. But what it shows is if you look at this drifter speed, you remove the long time mean, like I showed in the Atlantic, but better fields, more recent field, and you try to remove this wind-related component, it correlates fairly well with the anomaly from sea level maps. And this correlation is really related to the eddies. The eddies are followed, and also big current structure, which varies a lot, like the NECC in the tropics. But typically, correlations with all the noise there is in the data, the mapping issues, is typically at least on the order of 0.7. So it's a high correlation. 50% of the variance is common, despite many issues on the scales that are really resolved by both data sets. And the error in correcting Ekman drift. Now, to try to combine, there have been different approaches. I will talk about two. One is to estimate a geostrophic velocity, an optimal geostrophic velocity based on the velocity anomaly of from sea surface height mapped by Aviso. And you add the gain coefficients because the mapping kind of weakens. I mean, it's large-scale mappings, and the scales of the eddies actually are a little bit smoothed by this. So you know the currents are larger than what they measured on the maps. And you try to estimate an unbiased mean. And this unbiased mean is, these parameters are estimated locally to minimize by a square mean minimization, classical. So you do kind of, it's a synthetic current. You use the fact that there are enough colocalization of altimetry and surface drifts to correct and estimate a mean, which there is not actually in this altimetric field. That's one approach. And the second approach is to try to you do a synthetic mean combining different data in a slightly different way, and it's for Marie-Hélène Rio. Typically, and I will talk a little bit more of one part of that work and show some example of the mean field that she creates, and that can be added then to the anomalies from altimetry. But typically, you expect the currents to rotate because of this wind input, momentum input in the surface layer. You do a model of what this is. Seems that at 15 meters should be inversely proportional to something proportional, I mean, something a function of f of the Coriolis frequency, depending for the latitude dependence of Coriolis force, and a rotation, which is this theta. So you have a beta and theta. It happens that it's slightly better if you could take square root of f, so not the Ekman model, but something different. For these 15-meter currents, different authors have get that. And to do that, you want to filter in a right range of periods in which you can expect that to hold. So it's less than a month, basically, and it's longer than Coriolis frequency. And here they use ERA Ethereum to do that. And so we can estimate these beta maps, and I will show you them. Well, I show you them, sorry, it's inverted. That's the angle, the rotation angle in northern hemisphere winter, and look at the Atlantic, because in some ways the contrasts are a little larger and they are more certain in the Atlantic than in the Pacific, because of primarily the data in the Pacific. But you see that in winter, this angle is less actually, there's less rotation than in summer. It kind of makes sense because you expect with the increased stratification in summer that the Ekman layer diminishes and the rotation increases because you're deeper in the spiral in some way. And that's the variations of theta in the northern hemisphere and the inverse in the southern hemisphere. And there is little latitude dependence of this angle, little bit. It's hard to make sense with depths of mixed layer, actual depths of mixed layer, except you will see that the furthest north you go in the Atlantic, where really the mixed layer can be deep in this area in particular, and you get very small angles in winter. And it's a little bit more in area where it's shallower, like here or here. So, sorry. And by then you combine all the informations that you can collocate from altimetry in situ data, mostly the drifters, but not just the drifter, and you try also to use the geoids. That was an early attempt of 2009 where you used Fourier of Gray's data. And combining all that, this information, you build a synthetic geoid that's the average sea level height that you expect for, and I can't remember the years there, it's 10 years period. And you see for the Atlantic what we were seeing, you know, the gyre, the subtropical gyre structures, the boundary current and the recirculation of the Gulf Stream when it separates, and the southern subtropical gyre and much less recirculation in this area, confluence region, the subpolar gyre and so forth. And the cross gyre slopes when you're off the boundary, the western boundary area. And the uncertainties on that start to be small, and they decrease with time as the gravimetric data actually become more accurate with Gauche in particular. And then you have the surface currents from model. Here it's a free run, and I show it just to illustrate that, not surprisingly, when you go at high resolution, and in similar way as what you have in the altimetric data, you see a lot of eddies. Here I'm not plotting height, I'm plotting intensity of currents, but the currents are intense around the intense eddies. And what you see with all these wiggles are traces of eddy structure or fronts between eddies. And the ocean is filled with these eddies at any given time. That's an instantaneous snapshot. And you see also the meander of the main boundary current when they separate here, like for the Gulf Stream, or the recirculation after of the Agulhas return. And we have this last tool, which is the reanalysis, which use models like the one that was shown before, a free run. Actually, this one is a lower resolution, in which you try to assimilate all the altimetric data and the profile data up to now, as well as surface temperature. The currents are not yet assimilated directly into it. But the altimetry is absolute altimetry, so in that, the currents from the drifters enter. And that's the comparisons between the average zonal velocity from this model, and look at the Atlantic, with the average velocity from the drifters. So that run is from 1992 to 2009, the altimetric period. It's much harder to do this before that because you lose the strong constraint from the altimetry. And you see maybe a tendency to have slightly lesser velocities, but the patterns are fairly similar. And actually, in variability, when they collocate, they get also correlations on the order of 0.7, which were in the altimetry altogether at the beginning, so that's not surprising. But you start getting things which are fairly reasonable. Now, the fact that the currents are larger is probably that the product used contains data from drifters which are unfortunately undrugged. In the international database, up to now, there is 50% of data reported as drugs are not drugged, and that makes difference that can easily reach 10 centimeters per second in large areas of the world. So it's huge. There's a huge overestimate in these maps. Now, this is being redone, and the difference is much less. Currents are less in the new analysis of surface velocities. Compare, that's a product based on altimetry, as I was telling you, and that's what you see in glorious one. That's the eddy kinetic energy in the surface layer, so how much the currents vary locally. And of course, you see the large variations in the tropics and the large variations near the western boundary currents and the confluence area. They are more inglourious than in this product, which is based on altimetry. But as I say, the altimetry smoothes the small scales of the eddy, and therefore there's much less eddy kinetic energy than there is really, by factor 2 almost, except near the equator. And well, that's a general comment, but we know that these mesoscale eddies are generated by instability of large-scale flows to a large extent. And if you have a simulation which reproduces well the average currents, there's a good chance that it will reproduce also well the generation of these eddies, and will do also a better job at what the eddies should transport. Now, a comment on the transport by the eddies. In general, in oceanography, we have assumed in the past, I mean, not assumed, but it was fairly common assumption that away from the circumpolar current, heat and freshwater transport by eddies were very small. And that's true to a good extent. However, when going in models at high resolution or in this simulation, there is a transport when you start looking on isopycnal surfaces in the upper ocean or near 1,000 meters. You get a contribution of meridional transport, typically on the order of 10%, even at 30 north. So it's not completely negligible, but it's small. And there are areas where it's major, like here or near South Africa, of course. I'll talk a little about that, but I'm sure it will be talked again later on. And that's another example of comparisons of glories. That's the meridional overturning, also the transport in the upper layer, if you want, going northward. Based on this glories analysis, the dark line, that's the rapid MOCA measurements that Harry was showing earlier in red. And that's the cruises from, some of the cruises that Harry Bryden presented this morning. And the correlation is actually fairly high. It seems to be a small underestimation by 1 or 2 Sverdrup, but I think correlations on a monthly time scale is 0.8. So it seems to be a pretty good job when you do this kind of reanalysis. Now, whether here it's the periods where there were also after 2002 a lot of Argo floats which profile to 2,000 meters. Before that, there is less subsurface data, so I don't know whether it's as good for this earlier period than it is for the later period. But looking at the spectral characteristics of the variability, it's not different. When you look at the spectrum for this part and the spectrum for the recent part. So I suspect it's probably quite good. And that was the run without assimilation. And there you see that there were large differences. Correlation is a little bit less. It's not null, but it's much less. And there were a good 5 Sverdrup difference. So the assimilating the data has helped really making the simulation realistic and the transport associated realistic. So these can be tools to use to evaluate variability. Now, I will talk a little bit about things observed, variability observed in the South Atlantic before going north. And I will look successively at the confluence area, the subtropical gyre, where this separates the Brazil current and from the north branch and the south branch, and then a little bit the Agulhas current, but that will be for the later talk, so I'll talk too much about that. Now, we have a lot of drifter observations, but they tend to be more in the central part. But I will show for that area both estimates from drifter and from altimetry. That's the mean circulation from these drifters. And here you have the confluence zone. And overlaid over it and the mean current patterns is the trends over the changes of temperature, estimated as linear trend over a 10-year period. And something which is quite striking is, first, there's a maximum near the confluence area. We'll talk about that a little later. And then there are changes of sign which are fairly closely related to where the currents are. So it's not just an atmospheric pattern. When you start looking at this area of large variability in the west, you have an oceanographic pattern in the temperature changes. So you assume that there is a circulation change also when you see something like that. And then you have large scale patterns of temperature. That may be atmospherically forced. So that's the current Marianne Rios product showing an average of near 38 for the confluence area latitude, where the currents, the Malvinas currents and the Brazil currents meet. Malvinas currents, cold currents. Brazil current, the warm current from the north. And when you look at this region from the early 90s in the altimetry period, and also with the drifters, you see, and I can't remember which one is which, but anyway, the two show a tendency for a southern shift by more than 1 degree of latitude of this confluence region. And it has a seasonal cycle too, but it's true in both seasons, in most seasons. It's true in different products. I showed already the assisted trends, but and the idea about this is that the change of circulation here is changed a little bit like in North Atlantic, where we go from an hour minus to an hour plus, and you get this gyre somewhere in the northwest. Here you get something like that compared to the pattern. You displace the area of westerlies from periods to periods. And here in the northern part, you get anomalies easterlies, and that tend to shift the pattern of the gyre further south and move, at least in a very descriptive term. And we also have, simultaneous to this change of south, a general change seems to be of what the subtropical gyre structure has been, which has tended to be larger, increase in size over the last 15 years, based on this dynamic height pattern. That's overlaid. The color is the wind stress change. It's hard to see in that what forces this structure, but there is clearly a change in structure there also. And the change is also fairly linear. It depends how you compute it, but you get change which increases by, I think, roughly 20% per decade over the period. So it's less per decade, but over the 15 years. Now, it seems when you looked, and I forgot at the confluence area at least, you feel that from the 15 years data, there's a good correlation with a lag of about 1 year with the curl of the wind stress further east. So if you believe that, you can use the curl of the wind stress as a proxy, and that's what it gives you. So it has been shallow in the early mid-90s, and it has been further north and further south earlier and now. And that's the SST anomaly, which also show a pattern which is in opposite phase with that one, as you would expect from the change in latitude. And the weakening, the fact that the rotational is a weakening of the wind also. It's mostly that, I think, when you average over such a large area. But there seems to be a relation. I don't know whether climate models show things like that as modes of variability. And the other thing is that it's very low frequency. There is a very low frequency component to that. It's not related to SAM directly, because SAM has a linear tendency over that period. So it's more regional. That's SAM actually here. Whereas here we have a change in the middle. It seems that if there was a change, it would be later for SAM. I mean, I don't know. It needs to be observed and investigated into longer time series. What's frustrating when you look at the data actually is that the time series are too short really to be able to conclude on most of these phenomena. Time series variability is on too long time scales. On the other hand, when you look at the northern part of the gyre and you look at where the south equatorial current joins the coast, separate on North Brazil current and Brazil current, there is very little. There is very little variability of latitude. It seems to have been stable on the north end. Now I'll tell just a little bit about the Agulhas retroflexion, mostly the shading of eddies, but as I don't have too much time, I'll let that, and it will be it will be presented after. I will just show a few things, which is, well, we talk mostly of this area, now we'll talk here. And here, there seems to be, from model and analysis of data, a correlation between the latitude, the southward shift of the wind, which is really observed in the average by some index, if you want, in the recent decades, and increased leakage of this retroflexion. This leakage increasing happening mostly through this eddy, shading of eddies. And that's to get to this conclusion you have to do. I mean, these studies are based on analysis of data, but also uncased ocean simulations. Don't know what that is. These eddies that are shaded here, trajectories are represented, and they spread over a large part of the subtropical gyre. Here it's the census, the number. Of course, as you go further from the generation area, the number and the intensity of these eddies is weaker. Well, I already talked a little bit about that. I will not talk. When you do any cruise in this area, and that's the Bonus Good Hope cruise here in the near surface current in the surface layers, 350 meters, you see large, I mean, it's hard to see actually, but on the track, there are huge variations of the currents, which suggest actually crossing of two structures, one cyclonic and one anticyclonic. And if you look at anything like the potential temperature, you see this huge structure here, and you see also this structure for the north, for example, in the oxygen and salinity. So there is both an anticyclonic and a cyclonic structure here. Anticyclonic being kind of the retroflexion eddies. These eddies have huge transports. They also contribute largely to transport of salt, as was said this morning by Harry, and anthropogenic carbon, actually also, and oxygen in this ventilated layer towards the southeast subtropical Atlantic. That's where the core of the 8 sphere drop comes from. It's from generation 6 of 8 of these eddies a year. They're really huge. And they can have different routes. That's starting to be studied. I'm sure this will be talked again later on, so I'm not going to talk too much about that. And an eddy, when you follow a particular eddy like this one, the one that was crossed during the bonus Godot, you can see that this speed varies extremely along the track. It's not at all regular. It's very chaotic. Eddies, eddy dynamics are strongly influenced by encountering seamounts, topography, and structures of the currents. The point I want to make through that also is, in an area which is very eddy prone, you expect non-linearity to be able to also generate low frequency variability of the currents. And model simulations show modes, actually at high resolution, seem to show modes of variability of the southern ocean circulation, which are probably just related to interaction of eddy with the mean flow. It's very nonlinear. At a time scale of a few years to 10 years, maybe. It's not such a short scale, so that I will not talk. In the tropics, the focus has been much more on modes of variability, for example, the dipole mode between north and south. Here, it's a time series of the geostrophic current in the core of the north equatorial countercurrent here, around here. And it shows some low frequency variability, but a lot of seasonal variability that we knew already. And if you look at the error bars, you can see, however, that the error bars are fairly large. Now, when you combine with wind stress and information on where the ITCZ is, you expect to see some correlation. And I will not show exactly that, but that's the correlation here is, so that's standard deviation of temperature. Here's where the equatorial temperature index is estimated. That's called L3 in black. That's position of the ITCZ in green. And that's the difference, north-south difference of SST between area here and area here. And of course, the position of the ITCZ is much better correlated to this difference of temperature, because you expect a stronger contrast of atmospheric forcing also, and the feedback, the latent heat feedback, associated wind feedback associated to the change in the position of the ITCZ. But there is also an anti-correlation with the temperature in the equatorial. That's when I say north to south, that's south and that's north. Those are big boxes. And at L3, it's really equatorial upwelling, so it's different different processes, but there is also an anti-correlation. Well, we talked already about the large variability that is seen over the last few years, that Harry commented over the last few years. On the rapid line, here's an estimate of upper layer transport, really based on altimetry combined with temperature density profiles. And but what you see if you extend, that's my colleagues say, is that they suggest that there can be some large basin average circulation which come from the interior. That's Florida Strait transport over that period, Ekman transport here, and if you look at the interior, because of the eddies in particular, and changes of the intensity of the gyre and position of the gyre, you get fairly large variability. Not related to MOG directly, actually. It's fairly local, this variability. But it creates changes in the total integrated geostrophic transport. So there is a local forcing of MOG variability. MOG variability at this time scale is not necessarily related to changes in the Labrador Sea. It has to be also related to changes, more local changes. Can't remember why. I was showing the average, the new average altimetry, but you showed it already this morning. So. And then I will say a few words about data in the subpolar gyre. That's the average currents from the drifters, based on the drifters in the 1990s. And that's a simulation where they claimed they could see most of the branches of the northward transport of the NAC in the eastern basin. Now, as we've seen this morning, there's some suggestion that where the boundary, I mean, some of this water, when you look at the drifter in particular in the 1990s, none of the drifters that are launched in the warmer water really penetrates northward of this line. It's to some extent because of the Ekman current, but it's also because the warm water transport is mostly through the eastern part, the warmest water. Now, in recent years, there are two things which have changed. We have seen with the NAO change, you have less Ekman transport, so you expect more that the near-surface currents will be aligned with the geostrophic current and will mean more northward transport into the gyre. And there is a change, an associated change, retreat of the subpolar front, which probably gets closer to the west. So there has been suggestions from drifters that there is more drifters going there. Unfortunately, it's the same data set on which the presence of drug was not well documented, so I'm a bit suspicious. But I already talked about that. But we know from in addition to that doesn't show you that there is more. When you do an EOF like that and you look at the large-scale patterns, you don't see sign in geostrophic that there would be more, that the transport of warm water, there would be some cross-gyre transport. That doesn't show it. That shows here a change in circulation, and that shows a weakening. It's mostly the same area that was shown in the mean current, the main pattern for the subpolar gyre. So that shows you a weakening of the subpolar gyre. But we also know that fairly coincident with that, obviously not exactly coincident with that, otherwise it would be in the same EOF pattern, you have suggestion that the front, the subpolar front, so the area where the cold water recirculates, has retreated westward. So if this is the case, and if it's related to changes in the penetration of, more or less penetration of the warm water coming from further south into the subpolar gyre, an indication of what this variability could be of the subpolar gyre extent could be looked at from surface measurements of temperature and salinity in this area. So I just got at something I done a couple of years ago. Looking in the eastern part, the reason it's interesting is because we have data now spanning 110 years in this area. This is just one of the first area in which there was some effort to calibrate the standards used and make sure the data were correct. So that and in the Faroe-Shetland channel. It's the two areas. That was for merchant vessels, actually, going to Greenland and Iceland. So you don't have, at the time, they didn't go in winter, so you don't have the winter data. But if you look at this data for the other seasons, you can construct a time series starting in the 1890s, 1895 to now. And if you look at what number of grid points, here I selected a few grid points which are better. So the change of the subpolar front actually somewhere around here, and could have gone in very recent years, like I mean 1990s, mid-1990s here, and now would be somewhere here. So that kind of spans the area, the frontal area. So from east to west, you get to fresher water when you go along that line, fresher and colder water. So we looked at temperature and salinity, I was at density variability. Here I show an example for the summer seasons and the two seasons, spring and summer. And I will emphasize the low frequency variability over this period. What you see is some multi-decadal oscillations, decadal and multi-decadal oscillations. It tends to be fairly low frequency. I separated high frequency and low frequency near 10 years because there was a small gap in energy, or 10, 15 years. But that's just pure chance. Fairly coherent between seasons, and the same for S, a little bit less coherent. Oh, here, no, I showed just one season for S, which is this curve, and T is the other curve. I have to point because I forgot the color, figure with the color. One thing which is interesting is that there is a tendency for S to lag a little bit T. The two are very correlated, T and S variability. As you expect, if you have water mass, that it's a change of water mass expansion, so an indication of how far the water coming from further south go inside the gyre. And you have these periods in the around 1930s and in 1960s of high penetrations, like now, and periods in between, in particular around 1910, where there was the subpolar gyre was extending very far to the east, as well as in the 1980s and early 90s. But there was this earlier period. It's called, for some people, it's also the results of freshwater, an export for the Arctic, but that's less clear because we don't have the meteorological data near Spitsberg at the time. But there is this low frequency variability, and S is a little bit lag with respect to T, but in some ways, that's kind of expected because even if it's, well, I will come, if the forcing of the gyre is from the wind stress and the wind changes of NAO, the strong forcing is further west. When you go to the east, the gyre responds dynamically and thermodynamically, but it responds to things which to good extent are further west, those changes. And thus, temperature, if you have some advective temperature changes, it will be damped by the RC exchange. So you expect temperature to be a little damped, whereas salinity doesn't have this feedback. And the salinity is better tracer, probably, but the difference between temperature and salinity may be to the fact that T will peak earlier because afterwards it will be damped. When you overlay with NAO, and I will just comment on S, that S, the black line, and NAO, the dotted line, they are very, very correlated on this low frequency scale, so I say. Maybe with the lag, the correlation is maximal between 0 and 3 years lag, so that fits with the response of the gyre. So we may have indices from that, not from current measurements directly, but from indirect observation like these ones on what the changes have been on these lower frequencies. Because this could be also, I would expect here, and a few hydrographic data there from that time show also a very strong, there are only a few profiles. They suggest that there was a lot of deep Labrador seawater. But it's really basically based on 3 profiles, not the hundreds that Monica used. So there's interesting things. Now, when you see that, I mean, it's not clear whether it's, I mean, it's one realization of variability. You don't know whether it extends in the past. There's been suggestion that this kind of multi-decadal variations of NAO is not something that was so clear before these two cycles. But data are more sparse, of course, when you go to these longer timescales. So if I resume, with what we have tools to observe well surface observation and circulation, but mostly for the last 20 years. That's the kind of timescales on which we can say something really very, very directly. Because there we have we have the fields, we can resolve the eddies, and we have also model simulations, which can be also assimilating data and give some I mean, you can cross all those information to try to interpret the changes. And what we see in those is a lot of variability, which is at low frequencies, both on these gyro scales. I didn't talk about the eddy frequencies, but there are also changes in the eddy frequencies in different areas, and probably also in the role the eddies play in controlling the currents. Maybe more for the Antarctic circumpolar current, but most also for the Gulf Stream and other strong eddy area. And maybe, I mean, I don't know, maybe also for the Agulhas retroflexion and eddies shedding. That's something we'll probably hear about. We can extend, you know, but it's more empirical, the possibility to extend over longer timescales based on these recent data. And I guess when we extend, we do the same kind of work that paleoceanographers do. It's not different because we use proxies in some way of the circulation. We don't use things which are so direct. If you have a cruise, you know, a cruise every 5-10 years, you don't know so much what part of that is really related to I mean, what to attribute the variability you see. I mean, also a lot has been done and it's very helpful. Okay, well, I will maybe not talk about that. I think I spent my time.